private. These are also private. But the beauty about IP version 6 is you can have multiple IP addresses assigned to your network interface card. You can have a link local, which is just local within your segment. Okay. It doesn't go past the router. That's like an APIPA address or something. And then you also have a unique local that would go within your organization. And then you could have an actual globally routable, which starts with the 2000s to 3000s, okay? And that's globally routable, okay? Globally routable. So in this case, you got your private nets and the 10 net. Now, remember, this is a decimal. It's a decimal number, okay, with 3 digits with a period, right? That's the format for these IP version 4. In version 6, it's hexadecimal, which is a base 16 number, which is, 0 through 9 and then A through F. And it's 4 digits. So it's 4 digits with a colon, four hexadecimal digits with a colon in between. And then 4 more and a colon, and then 4 more and a colon, and so forth. And there's actually 8 sections that you have with IP version 6. So 1, you had a decimal number, and it was 3 digits with a period. Now you have hexadecimal, and in fact, it's really much bigger than that, because this big long number now is just this part is your network prefix, okay? And then you've got another set of 64 bits here that goes out. The last 64 bits are here.
Running out of room.
All right, so there's your network prefix, and that's the first 64 bits. And the final 64 bits is the actual client ID, okay, or interface ID. Okay, so, all right. So then, and in fact, you have some notes on this in Moodle. You can go to Moodle. And
what is the first section of 64 bits called again?
It's actually called the network prefix. And in fact,
the second part is the interface ID.
Yeah, let me pull this out. Let me show you this. Looks like this. No, it looks like this. Here we go. Okay, so here's your network prefix, the first digits here. Okay. First 48 are the global routing prefix, but this whole 64 bits of the 128-bit number is a network portion or network prefix. And the last portion is the interface ID. And this is specific to the individual user, okay? And they call it interface because really a user could have multiple NIC cards, and each NIC card could have its own interface or network interface card. And so you could assign these each to each one of those and go to a different subnet. But so it's kind of broken down into the first 64 bits and the second 64 bits to make up that 128-bit number. Right in the middle there, okay, is the subnet ID. Okay, so the subnet ID is the subnet. So where we used to have, if we have an IP address here, you had a separate, remember the subnet mask? That was, 255, 255, 255, right? That was a separate number. But the mask is built in. It's built in to IP version 6. So that's a big change. It's not two separate numbers for IP address, subnet mask to determine numbers of IP addresses and numbers of subnets, right, based on that mask. Now, it's literally built into it right there, that fourth, what they call a double octet, okay? Because it used to be an octet because it was 8 binary bits, but these hexadecimal numbers, each one of them is 4 bits each. So 4 times 4 is 16. It's a double octet. There's 16 binary bits in each one of these groups. And so, of course, 16 times 8 is 128. All right. So this subnet ID then can be, and what we'll talk about is they can only be a certain number. It's actually less than what it could be with an IP version 4 number. So with IP version 4, okay, then what we had is we had the ability to, remember our subnet mask could be, this one or this one or this one could be, 0. It could be 128, 192, 224, 240, 248, 252, 254, 255. Those are the options for these numbers in a subnet mask in IP version 4. Over here, you have a number, okay? And if you look at the number from the notes that we have in Moodle, and I should, where is Moodle? Okay, let's go down to this week, which is now April 13th. And okay, this is, okay, we got this, and I need to add, oh, it was on. Turn it off. And I have some notes that I will drag in here for you. And oh, I'm going to move it there, but I really wanted to move it all the way down to the bottom here. Sorry. Did I move it somewhere? No. You know what? I probably dropped it right back up to the top here. You know what? Just going to delete it. Go down to where I want it. Here. Okay, so in this week here, we've got IP version 6 addressing. This is the notes that I'm showing you on my screen in OneNote here, okay? So this subnet ID, each of these is, if this is 16 bits, binary bits, and then this is 16, this is 16, here's your first 48 bits, these first three groups of 4 hexadecimal numbers in an IP version 6 address. The next group there is from 48 bits to 64 bits, because that whole section, that first section is 64 bits. And then the interface ID on the end is always 64 bits. So once you have this networking segment, which includes a subnet mask, after that, the whole rest of this 64 bits is the IP address, the specific IP address for that node. And in IP version 4, when you change the mask, it changed the amount of subnets and it changed the number of IP addresses per that subnet. Do we remember this? How it did that? Just a little quick review here. Do you remember how that did that? So if I had a 151.155 class B address, and this was the 4 network, okay, and I had a mask here. If I just had this mask, then there would be 65,535 IP addresses and one subnet. And if I change that, okay, to a 128, which is that one there, then that makes 2 networks, 2 nets, and each of them is 32,000 apiece. And if I change it to a 192 right there, okay, that makes 4 nets, 4 networks of 16,000 apiece. See what I mean? So when you keep changing that, okay, in the end, if I go all the way up to the very highest, 255, that gives me 256 networks times 256 IP addresses, and that equals my 65,000 addresses. When I had one net, you know, and 65,535. So 256 by 256, 256 networks or subnets times 256 IP addresses per subnet, 254 usable, that equals 65,535. So the this mask here, this mask was changing the number of networks or subnets, and it was changing the amount of IP addresses per subnet. All right, is this coming back? Do you guys remember this now? Yay, nay?
Yeah, vaguely. Yeah.
Vaguely? Okay. Okay, well, with that, an IP version 6 address, 1, you know, see how these IP addresses were changing here, 65,032.16 down to 256 IP addresses? Well, in IP version 6, you always have the final 64 bits that you can use for your IP, for your subnet. It doesn't change. It's always 64 bits, which 2 to the 64 is what? It's a big number. What is that
It
number?
happens to coincide with your MAC address, but it doesn't have to be your MAC address.
Your MAC address is a 48-bit number. So it's a hexadecimal 48-bit number. But yeah, we're going to go over that because there's a difference in how you make a globally routable IP address. And that was another shortcoming of IP version 4. So if I do 64, okay, there's thousand, million, billion, trillion. Is it gazillion? What's after trillion?
Quadrillion.
18 quadrillion. No, what's after? That's quadrillion. Then what's after quadrillion?
Quintillion.
Quintillion.
Yeah.
18 quintillion. So 18 quintillion IP addresses for every subnet that you have. It never changes. So there was that confusion. Okay, in IP version 4, I changed the subnet. That changes the amount of IP addresses and it changes the number of IP addresses that I can use with that number they gave me. And now it's always the same. It's always 2 to the 64 bits is always the amount of IP addresses per subnet, never changes. And that's 18, what'd you say, quadrillion?
Quintillion.
Quintillion, 18 quintillion. Okay. So that's a better thing. So your subnet mask does not affect the number of IP addresses per subnet. Always 18 quintillion.
So you have the same 64 bits for trying to follow.
Yeah, you always have the same 64 bits.
For which part again?
The second half, which is the interface ID.
The nodes,
This last
the
64
interfaces.
bits.
Yep.
So if you've got this table here, can everybody see this table here?
So basically, if you use the same device but move to a different network, that part of the IP address would stay the same? Or is that what I'm getting at?
No, but you would get a different address because you'd be on a different subnet. If let's say you move buildings and you're on a different subnet, but what that means is when you move to another subnet with IP version 6, you still have 18 quintillion address possibilities in the new subnet, just like you did in the last subnet. That's all it means. This last 64 bits is going to be different, and so is the third double octet, that 1100 on there, that subnet ID. That's going to be different because that's going to give you the subnet that you're on. That's going to change, and then your specific IP address for your laptop would be different. Those last 4 groups of the interface ID would be unique to you in the new subnet, but the first 3 would be the global routing prefix would be the same.
So, okay, I'm just trying to having this difficult trying to track this
It's huge.
So we have the same number of options for the last 4, and then the first 3 remain the same.
Yeah, those are assigned to you.
Right. Or you purchase them.
Yeah.
If
Yeah, you
run a
register with
company.
the INA and pay your fee each year, and you get a range, and that range then is what then you can modify. You can modify then when the INA gives you that number from the group 4, and then of course the interface ID.
Yep.
And the same thing applies. You can use dynamic host configuration protocol. So where you were where you had DHCP over here, you have DHCP version 6. where you had DNS over here, you also have DNS over here, DNS version 6 to support IP version 6. All right. So these things still exist. You can still get a dynamic IP address. You still have name resolution and assigned to a IP version 6 IP address. All right. So if we take this number, that's your this long number now. Let's say it was 2001. This is your network network prefix, and you have 0, 3, 9A, and because there's 4 numbers here, and this is 0, 0, 0, 1, and this is 1100. That's your subnet right there. Okay, here's the first 64 bits, right? Here's your network prefix. Network prefix. Okay, and that's first 64 bit. And then the remaining, let's say your number was, you always have those colons. Okay. There's some rules that we have to go by with IP version 6. One is that you remove leading zeros because it's a very big, unwieldy number. So you remove every leading 0, okay? That means all these are leading zeros. This 0 right here, okay, is a leading 0. You can't remove those zeros because it's 1100, and that's part of the number. But anything that starts with a 0 can be removed. Okay, and so you can remove these 3, these 3, these 3, and these 3. So now the number becomes 20139A1, okay, 1100, and then 0, 0, 0, and then 1. So it's getting smaller, a little more manageable. So remove leading zeros is one of the rules. And then the next one is removing 4 zeros, okay? Or a double octet, it's removing 0 groups. And putting in a double colon in its place, okay? So it can be one set of zeros. This is one set here. This is another set of 4 zeros. This is another set of 4 zeros. And so it can be 1, 2, or 3 sets of zeros or more for that matter. But by doing that, these get removed. 2001, 39A1, 1100. And then I put 2 double colons, and 2 double colons is all that. Now this is your IP address. 2001, 39A, 1, 1100, and then you got 2 double colons and a 1. This is your, so that's not so unwieldy anymore by removing those sets of zeros. All right.
And then of course the addition to that rule is you can only do it once.
Yes.
You remove what one group.
Yes. Let's say this actually right here. let's say this was a 0 here. And so you wanted to put, you can't put here, you can't remove the 1, that 0, and you can't put 2 double colons. Okay, this does not work. That does not work because the computer, when it looks at that IP address, it says, okay, 1, 2, 1, 2, 3, 4. There's 4 groups left. Okay, out of 8 groups. But what is that? What do those double colons mean? Is the first double colon, is that 1 group of zeros, or is that 2 groups of zeros, or 3 groups of zeros? So is it 1 and 3, 2 and 2, 3 and 1? You see what I'm saying? It doesn't know how to break it out. So you can only use that double colon once in the address, and you have to choose. And the rule is you choose the bigger set. Obviously, the one on the right in the interface ID section, that's 3 groups of 4 zeros. So that's the biggest group. The one on the left in the network prefix was only one group of 4 zeros. And so you would put it on the one over there. So what you'd have to do instead of just those double colons there is you would just put a 0 right there. Okay, because you'd remove the leading zeros. So you'd remove the first 3 zeros, but you have to leave that as a placeholder to say, okay, that is a group of 4 zeros, and there's still 1 0 left as a placeholder. And then I know 1, 2, 3, 4, 5. There's 5 groups there. Now I know that those 2 those 2 colons right there, that equals the remaining 3 groups of 4 zeros that are not shown, because there's obviously 8 total groups and you only have 5 shown. So that double colon represents 3 sets of 4 zeros. Okay, does that make sense?
Mark, if I read you right, you're indicating that no matter what part of the octet that you're looking at with IPv6, you must have at least one placeholder 0 between each of the connecting colons, so to speak, in lieu of one of them being using the double colon. So you have to have placeholders at least with a single 0. And then you can just, yes, you can elect to use the double colons. And you're saying that if there was some sort of algorithm, you should replace the section of zeros that obviously has the largest number of those individual pieces of the octet, like those 3 zeros that you show up there. So yes. I got it.
Now, here's one final scenario. These 2 groups, sorry, I jumped the gun here. Let me pull this over here. Okay. This number now is 2001 colon 4 zeros colon 4 zeros colon 1100 colon 13 colon, and then 2 more sets of zeros colon 001. Now you have 2 sets of zeros over here in the interface ID section. And you've got 2 over here in the network prefix section. Okay, don't like my spelling. My network prefix section. So now what do? They're both the same size. There's 2 sets of zeros in the left group, and there's 2 sets over in the right part of this address. Okay, the rule is if they are the same, it should be the leftmost block of zeros. So in this case, the network prefix would win out in this case. And you would have, in this case, you would have a double colon over here on the left between 2001 and 1100. And then over here on the interface ID portion, you would have 2 zeros for placeholders because you still remove the leading zeros. And that would be your final number, 2001 double colon 1100 colon 0 colon 0 colon 0 colon 1. That would be your final number.
Isn't there
And
a
this-
13 in there somewhere?
Oh yeah. Sorry. Thank you. Yes, I had changed that. Well, it used to be 3 sets and now it's 2 sets. So it would be 13 colon 0 colon 0 colon 1. Yes, thank you. Yes. Okay. That's our final number. Yeah. And in this case, you know, since we changed it to a 13, obviously this 13 would be here, you know, up above as well. Okay.
Mark, can I interject a question? And I don't want to get ahead of your materials, so just tell me to hold on in case we're going to do that. When counting across this large 64 and 64 set, the subnet ID, as in the literature, shows 1100. I was taught that you are looking at hexadecimal with those addresses for IPv6, which means that you're at a base 16. So a lot of the new IPv6 addresses may have letter number combinations. So in the aspect of just the subnet portion of that, is that always going to be a numerical sequence and not include anything that might be alpha numeric?
No, that's not correct. See this, I'm writing it in hex. And in fact, this could have been, instead of a 13, it could have been A, B.
Okay, now that's in the interface ID. What about the subnet ID? Is
Oh,
it
here? Yeah, sure. It could be an A. Yeah.
okay? Okay, yeah. For some reason, when I see only the numeric portions listed that way, I wanted to make sure that I wasn't, because obviously the reason I asked that question is if you're just looking at IPv4s all day, all you're going to see is the decimal representations of those things are seen in binary. And it doesn't occur to you, obviously, that when you're generating the IPv6s, they're going to have as we've seen, all sorts of the letter number combinations. But in this particular case, I was wanting to make sure that there was not something I was missing in the subnet in comparison to its, previous subnet mask on the version 4. So I appreciate the clarification.
Yeah, from
Yeah.
what I've seen, the subnet prefix can be 16 bits. So any 16 bits you want to use. So so technically there could be 64,000 subnets for every
So when you're
internet routable
counting,
address.
yeah, when you're counting, I mean, it's obviously if you had 2 digits, it's 1, then it's 2, 3, and so forth, right? When you get to 9, then it becomes A, B, C, D, right? That's if this was 3 through 9, this is 10, 11, 12, 13. When you get to this is the last, so that's 14 and then 15.
You got to
Well,
add 00, right? You got to put 00 in the front.
Yeah, because this is the first number, 0, 0. There's your 16 numbers. It goes from 0 to 15. 0 is considered a number. So there's your base 16, 0 through 15. And then when you get to OF, well, what's 16 then? 16 is 1, 1 then.
1 0.
Oh, sorry. Yeah, 1 0. 1 0. There's 16. And so now you've got 16 and then 17, right? And as you go through that to 1 9, right? And then after that, what's going to be 1A, 1B, and so forth. So yeah. So what's when you get to the, if this was a 2-digit number, the very highest number is FF, right? Which again, is that 16 times 16?
Yep.
So 2 digits. Two hexadecimal digits is 256 with just 2 F's there. So 2 characters, what took 3 digits with a base 10 decimal to write 256. FF is 256 in hex.
Is it at 255? You got a -1 for it.
Oh,
If there's
I think you're right.
256, yeah. If there's
Because
256,
250, yeah, it's 255 because yes, when I times it together, it means there's 256 numbers, but one of them is a 0.
right.
So you're right. It's 0 through 255, which is 00, and then FF. So one's in decimal and one's in hex. You're right. That's exactly right. So that FF is 255. Yeah. Right.
You're getting into ordinal numbers versus the count of the, the total numbers. So yeah, I understand.
Yeah. Yeah. You got to keep me straight here. Okay. So now each one of these, if I have a A, I have a B and a 3 and a F. Each of these hexadecimal, here's a hexadecimal number. And of course, it's groups of 4. And each of these individual numbers is a nibble. A nibble is 4 bytes. Okay? Because 4 plus 4 plus 4 plus 4 is 16 bits. Right? And in binary, okay, in binary, if you break this down, again, everything breaks down into binary, just like our decimal number with IP version 4 broke down to binary. This A, when that breaks down, and A, what is A?
10.
That's 10. So if you have, this is the 1, 2, 4, 8. Okay, this is binary now. I know I'm starting to get angled here. Try and straighten it out. This is binary. Okay. Then you need to have, if that's worth 10, 8, 9, 10. There's 10. And then the next group of 4, the next nibble is this B, which is 11. So 1, 0, 1, 1. That's 11. And 3 would be 0, 0, 1, 1. Okay. Because that is the 2 and the 1. 2 plus the 1. 2 plus 1 equals 3, right? So just simple binary math here. So that's the 2's column and the 1's column. And then this last one is what?
1, 1, 1, 1.
That's right. That is the maximum. And so to be all ones in binary, that's the maximum or highest number in a base 16. So 4 ones is an F. All right, that's 15. And that's why it takes 4 binary bits to actually support those numbers, because they can go up to 4 ones as the maximum number with hexadecimal. So with hex here, you're looking at that, and below it, you've got your binary breakdown. And that's why it's a double octet, or 16 bits. An octet's 8 bits. And each one of these letters is a nibble, which is 4 binary bits. All right, so that's how they break it down with hexadecimal.
That's why they use hex, is because it's an easy conversion to binary. So the machines can
Yes.
can do math on it easy.
So now that we've got that down, let's look back at the let's look back up here at this, or I guess I can just pull it up here. Let me pull the spec across so it's a little bit cleaner. Okay, let's look at this subnet ID in the middle here. It's the last double octet of the network prefix, the first 64 bits. It goes from 48 bits to 64 bits. That 16 bits is allocated to the subnet ID. In this case, I used 1100 here. All right. And so the same thing applies. All right. With, and this is removing 0 groups, but it's called, the technical term is zero compression, is what it is. Okay. Zero compression. When we use those double quotes, okay? So let's take the, let's take this, what was an 1100 here.
Hey, Mark. So you just want to clarify. So double zero compression is the double colon.
Yes, the double colons, yeah. And then remove leading zeros is the other one where you just remove, you always remove 1, 2, or 3 zeros. Sometimes you have to have a placeholder, and you can't use zero compression because you've already used it somewhere else in the number. So you just remove the leading zeros that are remaining. So you just have a 0 in that spot.
I mean, just out of curiosity, why IPv4 is using comma and v6 is using zero compression?
So with IP version 4, there was no compression. Well, I guess there was, you didn't have to have the placeholder. You, it was just, if there was a 0 there, you just didn't put the 0. But with the hexadecimal number, they made sure that you remove the leading zeros as a rule, because the number is so unwieldy. And that way, if you stick to those rules, remove leading zeros and zero compression, then if you have a database of IP version 6 numbers and you search for a number, you have to make sure that you have those rules in place, because searching for the number, this first number, okay, if you search for this number here, and it's, 1100 here, and you search for this number, and it's in your database as this number, right? You know what I mean? If it's in your database as that number, then you've got a problem, because if you search for 2001:0000:0000:1100, that's a different number than 2001:1100:13:0:0:1. So you have to make sure that all your numbers follow those rules, so that when you do a search for the zero compression and leading zeros removed number. Does that make sense?
All right. Yeah, it's like the law or the rule that they made for IPv6, I guess.
Yeah.
The computer's got
Okay,
to do
yeah.
the math to expand it back out.
Okay, great. Thank you.
I mean, technically, those two numbers right there do the same thing. Those two are the same numbers. But the second one has done remove the leading zeros and zero compression, and searching for that second number would not find the first number. Yeah. But you're right. The computers are built in with the IP version 6 stack that when it converts to binary, okay, you still have all the zeros represented with four zeros in binary.
Mark, this just opened up a small can of worms for me, and I'll tell you where I'm coming from. I love the idea that IPv6 can shrink, compress, and of course save bandwidth on any leading zeros or any group of zeros. But you're indicating that in the case of a database where it's actually holding the uncompressed address as the explicit address that's assigned, you're saying that the software or whatever operating system is still not been standardized to uncompress the address before the database software gets it. Also, too, I'm thinking that all the IPv4s, if you're converting one way from IPv4 up to an IPv6, that might indicate an age or an obsolescence factor where the IPv4 had to be reset into the IPv6 framework. But that also would have you taking off a lot of leading characters because, as I mentioned earlier with the numerics, you don't have the same length of an address as you do with a standard IPv4. I'm getting ahead of myself, but then the third thing is, which I've never asked anybody this question, is that with all of these changes to convert, which means that is possible that you cannot convert an explicit IPv6 into any kind of IPv4 without standardizing how they would have to do that for maybe older software?
Right. So first off, I'll answer this question. I'll jump in here. Okay, so your database is going to have the compressed version in there. It's not going to have the uncompressed. So the computer is going to look for an uncompressed one. So it's going to have to uncompress the database version in order to match them. Does that make sense?
Yes, it does.
Okay. So that clears up that part of the question. The other part of the question that you asked so IP version 4 and IP version 6 are completely incompatible with each other. They have nothing in common whatsoever. Okay. So yeah.
Yeah.
I'm only asking about that separate question because it seems to me that there were some converters that they have tried to establish that would just simply take the
several
numbers.
RFCs out there that have attempted to marry the two, but at their heart, they're completely separate.
You saved my life. I'm going to toss that. I won't.
Yeah.
Okay.
If you go to network, you do control panel.
And then, so next period, we are going to talk about dual stack and how you use that and why you'd use that and what's the benefits, what's the disadvantages, that type of thing.
Okay.
All right.
So, go ahead, Mark.
So if this is 16 bits plus 16 bits plus 16 bits, here's your first 48 bits. Now, each of these, of course, is equal to 4 bits each. So now we have 52, because 4 bits for this guy, okay? 56, 60 for this one, and then for this one, 64. Each of these is 4 bits each, these in this subnet, okay? So when you get a number assigned to you from the IANA, it's an assigning registry of IP addresses and ports and other things. The official
Oh, right.
company that you can have an IP address that is a /48, a /52 /56, a /60, or a /64. This is the CIDR notation. And so if you get a number, let's say the number from the registry that you need a grouping for St. Martin's, and they want to migrate to IPv6. So Peter requests a IP version 6 subnet, okay, and he gets 2001, 39A 6B 1C, and then he gets 0, 0, 0, 0. Okay, that's what he gets, and he gets that number. Okay, and out here they give it to him 2001 39A colon 6B1C /64. That's the number he gets for St. Martin's. So what that means is this subnet section right here then, okay, this subnet, he can modify all of these bits into subnets for St. Martin's. Well, each of those is 4 bits each. 4 plus 4 is 16. 2 to the 16 is what?
64,536, I think.
Yeah. He has, okay,
65,000.
he has all of these 2 to the 16, which equals 65,536. Okay,
Now, that'd be
so
if I signed up for a /48 though.
if you sign up for what?
A /48.
Yes.
Okay.
Yeah. So he's got 65,536 subnets. You know how when you did with the CIDR notation, it changed the number of IP addresses? This is just subnets because the remaining 64 bits always stays the same. All right. And so you get 18 quintillion IP addresses for every one of those 65,000 subnets. So Peter has the ability to create 65,000 subnets, each subnet with 18 quintillion IP address combinations. So let's say he says, well, I don't really need that many. Maybe I should request a 52, a /52. So the number they give him now is something else. Okay, they give him 2001 39A 6B1C colon, and they give him, maybe that's an A there. And then there's 3 zeros, and instead of a, sorry, not 64, 48. Now it's 52. So this A there, he cannot modify because it's a /52. But now he can modify the remaining. Okay, now I can modify the remaining three remaining placeholders for hexadecimal. And that each of those is 4 binary bits. So that's 2 to the 12, right? 4 plus 4 plus 4. All right. And 2 to the 12 is what?
96.
96 subnets. So he could have 4,000 subnets on St. Martin's campus. That seems a little excessive. Probably will not ever hit 4,000 subnets, but that's possible. So maybe he requests a /56. Again, he gives that one, and that is A, C or something. Who knows what they give him? He can't modify these first two. He can only modify the remaining 2, okay, zeros. All right, right there. That's all he can modify. So now it winds up being a /56 is 2, 2, because 56 is right there, okay? He can modify those 2 digits. 4 plus 4 is 8. 2 to the power of 8.
256.
256. Okay, he might actually get 256 because a /60 then is only 2 to the 4, right? Which is and the final /64 there, okay. Okay, after the /60 is 2 to the 1, which equals 1 subnet. So for St. Martin's, he doesn't need one massive subnet of 18 quintillion. He wants to subdivide it. So 16 is too few. He's got to go to at least a /56 or higher for St. Martin's. So he would request maybe a /56 and get 256 subnets. Every subnet of those 256 that he creates always has 18 quintillion IP addresses to utilize. So he's never going to run out of IP addresses on every subnet. He never has to worry about it with like IP version 4. You kept subnetting it down, and all of a sudden you got down to 32 IP addresses or 64 IP addresses or 128, right? You had to be careful. That's never going to happen with IP version 6. Are people seeing that? Are people understanding that? Does that make sense?
I think it does, Mark. I think you pointed out in this application of using the CIDR notation for IPv6. I do have a question as to like an example that you show where you've got the A and the C there in those first two, those 2 bit slots there. That means it's going to be actually static. There's no mix and match on those first 2 positions. You're not getting those. You're only going to get the other.
Exactly. He
Okay.
got this number 2001:398/6B1C :AC00 with a /56. Okay.
Yeah.
So now
I
with
would,
that /56, he can only modify every subnet that he creates at St. Martin's will start out with AC. AC01, AC, you know what I mean? AC02, that's your 2net. You know what I mean? AC03, you know what I mean? Once he gets up to AC09, that's, you know what I mean? Then he's going to go AC0A. You see what I mean? So
Yeah.
he can only
you make
modify.
it very clear that with the other IPv4 masking, you were watching the address limitations be reduced as the CIDR kept expanding the number for the subnet for IPv4. In this case, they're 2 totally separate things. You're keeping 18 quillion no matter what subnet restriction that you're going to get. So
correct.
That's good.
Yes, exactly.
And so I would go to the ARIN.org, American Registry for Internet Numbers, and they would give me whatever / I would sign up for. So,
Do you gentlemen know whether they can be reassigned or are those lifetime numbers?
You have to sign up for them every year. You have to renew it every year.
Okay.
So
You have to pay your money. And if
You
you
gotta
don't, then you
pay.
lose that range.
you got to make the money.
Oh
It's
man, I don't think we have an
registered.
internet unless it was there like that. I know getting your websites, people learn early about having to pay for renewals. So
Yeah. Just like our IP version 4, same company or organization does it for IP version 4, and we have to pay for the publicly routable IP version 4 ranges that St. Martin's has, and those are registered under St. Martin's, but a specific name, contact. I think it's actually, is it Neil or is it you, Peter?
It'd be me.
Yeah, it'd be under Peter.
Yeah.
Peter would have his contact and IP address. So if they have a question about it, or they get an IP address that comes from that range, they call Peter.
Yeah.
It's got a problem.
So, and then I think most ISPs, if you request an IP version 6 address, they'll give one to you free because there's just that many of them.
okay, I've beat you guys up, but I'm thinking about how we all communicate over the web with, with the IP packets. So the adoption of an IPv6 as a standard, how does that affect not just the RFCs, but the ISOs and things that deal with sending information across the web? I mean, are we going to see software that has to basically be certified IPv6 and applications, certified for that? Because I can only assume that even though it's compressible, there are issues with the way a packet would be formed with this format.
You have
You
to
are
design
absolutely-
that
Yep.
software to support that IPv6 stack. That's right.
Yep. That's why they have DHCP version 6, DNS version 6,
So
and pretty much
Peter,
everything, every other application out there has to have version 6.
yeah, Peter wants to go to IPv6. He's got to verify that every printer on campus supports IPv6. Every application supports IPv6. Every voice over IP phone, every wireless access point, every switch, router, every device and every software application has got to support IP version 6.
Yep.
It's a huge undertaking.
Okay, that leaves me with an Intel question for you, Mark. I mean, error correction used to be a big thing when you're transferring data. Here we are with these newly expanded packets, and we may not talk about it in this networking class, and if so, then just tell me to divert that question. But how is it that we can adapt in error correction or figuring out whether we're losing bits or things with an expanded address situation?
Actually, I think the header itself is smaller.
Yeah.
Than the IP version
but
header.
the bits still remain. You verify that the packet that's being sent across the network in IPv6, same as IPv4, that when you get to the end, is it the same size as when it started? If it's not, and your cyclical redundancy check, CRC, says a different number than what the packet size is, then you resend the packet. So TCP rules and segmentation, reassembly, those still apply with IPv6. It's just that you have a 128-bit number now that your router software has got to figure out, oh, this IP number is a valid IP address, right? It's got to understand the rules of IPv6.
Yep. And if it does, then it actually has less overhead for routing purposes than IP version 4. So it's a little more efficient.
Yeah. So in that that document, you've got IP6 packet format has been streamlined. Header segments that never were used have been replaced. So actually running IPv6 is easier to route, is simpler and is more streamlined. It's more efficient. There's a lot of benefits to this. So this is all in your notes that we dropped in this about today. Here's the comparison between these. 4 groups of octets, 8 groups of double octets, decimal notation with 3 digits separated by periods, hexadecimal separated by colons, 32-bit, 128-bit number. Okay, separate subnet mask, integrated subnet mask right here. Okay. A PIPA when you don't get an IP address, now we've got brains in IPv6. When Peter talks about it, he's going to talk about stateless address auto configuration. Next time, how to create a globally routable IP address when you don't get a DHCP address. Okay, one address, one IP address per NIC, multiple. Link local, globally routable. You can have multiple IP addresses per interface. Network address translation. You got to translate from a private to a public. No NAT required because you always have a globally routable IP address for every single device. You're not going to run out of IP addresses. So that streamlines and makes routing more efficient. Broadcast, there is no broadcast anymore. It's multicast. Peter will talk about that. DHCP version 6, DNS quad record, IPv6, IP6.ARPA. And then IPsec was an add-on, but IP security is built into IP version 6. So,
I got a quick question. So if just out of my mind, just out of curiosity right now, would it be okay to use IPv6 as a public IP, but in your private IP side, can you stick with IPv4?
Yeah, you can.
That way, then why would you need to verify every single devices in your, like for example, if
you
Peter
wanted to go pure IP version 6, then yeah, you'd have to do all that.
but if you can still stick with the IPv4 for the private side.
but you
They
got
do
to
have
have
a
some type of translator from
Yep.
6 to 4. You've got to have a tunneling protocol to convert between 6 to 4. And there's different
Okay.
tunneling protocols that are available for that.
It is possible. It's a pain in the butt, but it is possible.
Oh, it's hard to configure or translate it,
Yes.
I guess.
Yes.
Got it. I see that result. So my second question, and you mentioned that anyone can ask for IPv6 since there are too many outside. Would it be available for personal uses too?
Yeah, that's what I meant. Like for your own house, personal use. Yeah.
Oh,
You
okay.
You can contact your ISP, and they like Comcast, they'll give you one for free.
I see. Great. Okay. Thank you.
Mark, I want to thank you for having all those colors on those notes I just printed. I think my printer's now out of colored ink on that on that one page. But we're good. I needed that, so that was really good. I don't know if you want to cover it today. I had the very last thing I was going to ask is that if he's going to go over a lot of these comparisons, that one of the things I had about DNS stuff is that there's when we talk about globally usable, there was some discussion a few years ago about global DNS authorities, about who really controls where you resolve some of your addresses and so on. Will there be any coverage in this class on maybe addressing, shall we say, other side of the planet trying to control some of the DNS resolution systems? For example, if you just type in the name of a website, I had in my lifetime an incident where my particular email account and one of the websites that we brought up corresponded to a site in China. And there was some issue about them contesting actually resolving some of the names to some of the websites that we had set up at that time, although I've never had that problem since. So I don't know if that's been something that the international community has already worked out. I don't know.
There was a problem with DNS hacking where they redirected some DNS addresses, but yeah, they've tightened the security on that. So
okay,
Just like there's IP security or IPsec, there's also DNSSEC. There's a secure version of DNS that can be implemented. IP and DNS and other FTP and Telnet, these were original communication protocols or remote access protocols that had no security whatsoever. Your passwords went across in plain text. If somebody was in the middle and captured that, they'd have your username and password. So over time, we've added security into all these things, including DNS and IP and whatnot.
yeah,
perfect. Thank you.
For example, Telnet. Don't ever do Telnet across the network, across the internet.
I think only Congress still uses Telnet, Peter. I think they're the only ones who are still having their aides use. Yeah. Yeah.
All right,
Thank
everyone.
you for that.
Thanks for being here. We can stop the recording, and if people want to stay and talk a little bit longer, we're happy to talk longer, but we